1877, two scientists published the most complete picture of the ocean floor that had ever been created, revolutionizing our understanding of the Earth. Named the Tharp-Heezen map after its collaborators, this illustration was produced using sonar and measurements of the water's depth. It revealed for the first time a complex network of underwater mountains and ridges, and provided key evidence that supported the emerging geological theory of plate tectonics. This theory states that the Earth's solid outer shell, the lithosphere, is broken into plates. These plates shift and slide over the asthenosphere, the molten upper portion of the mantle. Oceanic and continental plates meet and interact at boundaries that crisscross our planet. Because 71% of the Earth is covered with water, the majority of boundaries are found on the seafloor. When two oceanic plates tear apart from each other at a divergent plate boundary, the space between the divergent plates fills with magma that hardened when exposed to cold seawater. Over millions of years, this process has built chains of underwater volcanoes and rift valleys called the mid-ocean ridge.
When the plates move apart, they rip open the Earth. The mid-ocean ridge, which runs around our planet like the seam on a baseball, where the Earth creates its outer skin. And as these plates move, they're in a synchronized ballet.
There are few places on Earth where the mid-oceanic ridge rises out of the ocean, giving us a chance to see this phenomenon on dry land. Iceland is one of them. The island of Iceland was once an underwater section of the mid-ocean ridge. Over millions of years, it was pushed up above sea level by a giant volcanic hotspot. Here, we can see a divergent plate boundary, a stretch of the mid-Atlantic ridge where the North American and Eurasian plates are spreading or rifting apart. Geologist and oceanographer Dr. Bob Ballard has come to this unique spot where crystal clear glacier water has filled a section of the mid-ocean ridge that has been raised above sea level.
Boy, that's truly amazing. I'm literally at the boundary of creation in Iceland. On my left is the North American plate right here. I can put my hand on North American. I can reach over here and put my hand on the Eurasian plate. And this is the very spot where the Earth is spreading open about an inch a year, about your height in your lifetime.
When two plates are spreading apart in one section of the world, other plates are moving toward each other in a different area, forming a convergent plate boundary. At these kinds of plate boundaries, one plate can slide underneath the other in a process called subduction. Or, the two plates can crash into each other, creating a mountain range. The Himalayan mountains formed this way when two continental plates collided. On the Mediterranean island of Cyprus, we find an example of a convergent plate boundary that was raised above sea level 90 million years ago as the African and Eurasian plates collided. Dr. Ballard has come to explore this unique part of the mid-ocean ridge in the light of day.
I'm standing on what was an ancient ocean floor, would have been thousands of feet beneath the sea. What we're looking at is an area where the subsequent collision of these great plates, the African plate and the Eurasian plate, then began to force this part of the ocean floor up to where it is today.
This upward movement revealed ancient volcanic activity that had taken place on the ocean floor.
If you look into that upper section, you'll see these round little...
Yeah, perhaps I'm not so interested in that first. So this is a primer, if you've never seen anything about plate tectonics, to understand that there are constructive boundaries, mid-Atlantic ridges, where magma floats up between them, pushes them apart. Bob Ballard is quite a famous guy. He is the person who ran the Glomar Explorer, the CIA ship that was produced with an open bottom to go and look for in the Cold War, a downed, not really a downed, Russian submarine which sat in the middle of the Pacific, which had imploded, to go and recover it, to get intelligence. And so the ruse that he put together with his group from the US government was to have an idea that we'll have a ship, we'll have that ship go off to sea to do nodule mining offshore, we'll get investors in that ship, but all the time the purpose of that was to go into the ocean, be able to pluck out this Russian submarine and then take it home clandestinely to be able to do that. He also might be the guy who went and discovered the Titanic, the most recent recovery of the Titanic. So anyway, he's an interesting guy. I remember we took students to this place in Iceland. It's called Thingvellir. It used to be the site of their ancient parliament. It's where the island and the earth is splitting apart. Eurasian plate on one side and North American plate on the other. You can't see it moving. I liked his simile that he had provided of it moves by about an inch a year, about your height in your lifetime, 60 inches in 60 years or so, which is about right. And our interest in plate tectonics is in understanding the distribution of high heat flow areas within the world. I think we talked last time about the fact that those high heat flow areas are typically on plate boundaries. Those are hydrothermal systems, which have the advantage of the fact that the temperature is elevated high within the crust at those regions, but also that the permeability of those rocks is super high because they're being fractured, either being pulled apart, as in Iceland, or being crushed by convergent boundaries, which make the fact that you can push fluids through them to be able to act as a heat exchange fluid to actually recover the heat from them in geothermal systems. And so the interesting thing about hydrothermal reservoirs is that they exist, pretty much those resources are all used up because they're the low-hanging fruit. And we'll talk about those, but we'll talk about more difficult to utilize sources, which are actually a much larger resource, but are actually a much more challenging to be able to recover from the subsurface. So that's the plan for today. So I thought I'd introduce it with that particular deal. These are the notes that you have that you can download off the webpage. You should be ready now with the modality of this class. I sent an email to some people who might have joined late to get them to do lecture 1-2 online if you weren't here in the class on Thursday. And then everything else, if you're in the class, you need to do the other quizzes, but not the lecture quizzes. So hopefully everyone should be up and on guard with that. So often it's useful to kind of recap what we talked about last time, even though we started talking about plate boundaries already. We talked about the big picture for energy, the fact that we live on something like a 500 exajoule planet in terms of annual energy budget. The US uses maybe 20% of that, 100 exajoules, 100 quads, 100 trillion cubic feet of natural gas equivalent. They're all roughly the same. The different sources of that energy would be fossil fuels, coal, oil, and natural gas. Natural gas most commonly in the subsurface in reservoirs, either as conventional reservoirs, Gulf of Mexico, or unconventional reservoirs such as gas shales. They are relatively large reserves worldwide. I don't think they're as big as hydrates. Hydrates are the burning ice, which may exist at 10 to the 6 exajoules in terms of reserves. The geothermal reserve is actually huge also. I mentioned last time also that the hydrate reserve is kind of curious in that it shrinks with time as we know more about its limited saturation on the continental shelves. It's there much smaller proportions than we initially thought. But the geothermal reserve is quite large. It's 10 times larger than that, at least 10 to the 7 exajoules. So if the worldwide budget is 500 exajoules per year, then 1,000 exajoules would be for every 2 years. So that would be 10 to the 2 times 10 to the 4 years that would supply. So the reserve is huge if you can tap it. It's not very easy to tap because it's not really recoverable. The hydrothermal reserve is much smaller than that. It's something like 10,000 exajoules. So in other words, for 2 years that'd be 1,000 exajoules. So that's 1,000 years of hydrothermal power to power the world. We talked last time, I don't know why it wants to do that. Does this come up? We talked last time that the current capacity in the US per annum was 0.2 exajoules. And Josh asked the question of what exactly is that in the capacity of in terms of a generation capacity. So 500 exajoules is something like 10 terawatts in terms of power. One is energy per unit time, which is a year. 10 terawatts is power. So this would be 0.2 exajoules. That was on our Sankey chart, divided by 365 times 24 hours a day times 60 minutes an hour times 60 seconds a minute. And does it get larger if I make it larger? Does it get larger? So that is, so the 0 is there. So this is mega, this is 6.5 gigawatts. Yeah. So we said last time that the geysers is something like 1 gigawatt capacity in terms of this location in California. So, and I did look it up. You can look it up very easily on Gemini or just AI. It comes up, I thought it said it was 4 gigawatts capacity in the US between all the different places. So it would be mainly in the geysers, which is the largest geothermal field in the world, hydrothermal field on the west coast of the US, just 100 kilometers northeast of San Francisco. And the size of it is relatively large. It's a hydrothermal field. So that's kind of putting geothermal energy into perspective in terms of the amounts. These motivation portions, I'm not sure why I have that in these, but you will see I will use these. So I'm not sure this matters. But what we're interested in talking about is in terms of our behavior for these different sources. So different forms of geothermal energy that we can look at span, if you like, from the best to the worst. Or most optimal to suboptimal. So the ones which are the dwindling reserve, which are pretty much utilized, would be those that exist where both water is present within the system, but also porosity, so that you can plan on recovering the heated water directly from the system because it's already saturated at relatively high porosities, maybe at 20 or 30% porosity. Recover the heat from it, do what you want with it. Usually the heat at these plate boundaries is high enough, maybe 200 degrees centigrade at a few kilometers depth, that you can certainly flash it to steam and convert it to electricity, and then to stop the reservoir from being depleted hydraulically by fluids, re-inject the fluid at some other distant location far enough away from where you're recovering it so that you don't cool your recovery wells and therefore kill your geothermal field. So those that exist in volcanic regions and on plate boundaries would be the hottest, maybe something of the order of greater than 200 degrees centigrade. And of course, from that, you only need to get to 100 degrees centigrade to be able to flash to steam and then use the vapor to produce electricity. If you look at reservoirs that are sedimentary reservoirs, so they might just be deep reservoirs in sediments, porous sediments, or they might be petroleum reservoirs where you're recovering water along with the hydrocarbons, and you can use that hot water, such as they do in the Williston Basin in North Dakota, to be able to scavenge 80-degree heat out of that and be able to do something with it. If you have a town nearby, you could use that for district heating, direct heating of space within the system. Again, recover it, and then once you have this brine on surface and you've cooled it down, you want to re-inject it so you don't have to dispose of it in any other way. It's most convenient if you can re-inject it back into the same reservoir. And then so-called hot wet rocks and so-called hot dry rocks. So hot wet rocks would be where you have some porosity and some native fluids in presence. They may be just as hot as these hydrothermal systems, or they may be cooler. But the point is that porosity exists in these to be able to recover the fluids directly, and these are not necessarily sediments, they're typically in crystalline rocks. And so these are also cases where you need enough native porosity in these otherwise low permeability rocks to be able to recover the fluids from them, and those fluids will carry the thermal energy with them. And by far the majority of this very large reserve, so we're talking about in the US, this huge reserve of heat at depth is something like 10 to the 7 exajoules. Exajoule is 10 to the 18 joules, is this. And so to do that, you need to be able to make permeability in this where it didn't exist, much the same as if you want to recover gas from shale gas from gas shales. You have to create a reservoir with high permeability to be able to have a large surface area to be able to recover the gas shales from it. However, for unconventional geothermal reservoirs, which is what they are, unconventional means that they don't exist with existing permeability, it's a much more difficult problem, because if you create porosity in gas shales, you can just suck out the gas which is liberated and take it up to the surface. If you want to recover heat from an unconventional reservoir where you first have to make the permeability, you have to make a distributed network of fractures somehow that you'll then circulate cold water into, and then across the reservoir and back out through a recovery borehole. And so that means that not only are you just receiving what comes to you, you actually have to actively make sure that the sweep that you get through this reservoir is able to contact enough heat surface area that it and stays in there, the water stays in there for long enough that it's able to heat up and come out hot, rather than just going in cold and coming back cold if it doesn't have sufficient heat surface area to come across it. So that's the issue. So the challenges in terms of these reservoirs go from easy on the left to much more difficult on the right. We can define the behavior of these reservoirs in terms of their productivity, and we can define that in terms of a heat rate, which is equal to a volumetric flow rate, the density of the fluid, the specific heat capacity of the transfer fluid, and the temperature of the fluid as it comes out of the system. So the heat rate would be in terms of power, so that would be in terms of watts, which is equal to joules per second, which is Newton meters per second. And that is a function of this parameter here. And this we could also think of in terms of a mass flow rate. So I use this terminology m dot, which is just equal to a change in mass per unit time, a normal engineering method of saying that. This would be volumetric flow rate. So this would be in meters cubed a second. This would be density. This is kilograms per second. This is specific heat capacity. And that is in units, well, for water, so for H2O, which would be a typical heat transfer fluid, it is equal to 4,000, I think 138 joules per kilogram per degree C, or degree Kelvin, I guess. It's, so 4.13 joules per gram per degree Kelvin. And temperature would be the change in temperature between inlet and outlet. So this would be the temperature. It might go in at surface temperature. So surface temperature might be 20 degrees C or 30 or 40 degrees centigrade if you're in Nevada and you can't cool it off. It would be the old water that you've removed, that you've cooled down by taking the heat out of it to be able to scavenge the heat before you re-inject it. And the recovered heat might be the order of something like, so if this is 200 degrees centigrade and the injection is 40, then it would be 160 degrees centigrade, would be the delta T. So the magnitude of the heat that you can recover from this is going to be a function of these parameters. And so if we understand that, we could actually do a very quick calculation. Heat rate is going to be equal to what? We said last time, actually let's go back to it just to remind ourselves. So the viability of any geothermal energy, and this is quite an important feature, we looked at this figure last time. This red line defines the minimum output you need from a well to be able to drill it. Drills cost maybe $10 million for a 3 or 4 kilometer well. It gets more expensive as you go even deeper because of tripping costs. But the break-even cost for a geothermal well is something of the order of 100 kilograms of water per second per well. And the reason for that is that the payback is that you need something like 5 megawatts of electricity per well to be able to pay off over a 20 or 30 year lifetime this $10 million that you've invested in a well. If you look at the right-hand spectrum of geothermal projects, the hot dry rocks or enhanced geothermal systems, the earliest one was Fenton Hill at Los Alamos National Lab in the early 1970s, 1974 it originated, but this is a bit later. And a second stimulation of that, one in the UK, 2 of them in Japan, the Sulz project, which still runs between France and Germany, and projects in Nevada, Desert Peak, in Southern California at COSO, back in Europe again, and Cooper Basin, which is now a defunct project in the Cooper Basin in Australia. So actually the only one of these which is still running are the Sulz project, which is here, these 2, both of these, or all 3 I guess, these different, all in the same location. And the desire is to be able to get above this threshold. So the reason for that threshold defines exactly the behavior that you need to get out of your reservoir. So if we go through the math on this and look at what this is, so the volumetric flow rate is in meters cubed per second. The density of the fluid is water, which is 1,000 cubic meters per second. So this whole term, so what would that be? To get 100 kilograms a second, this would be 0.1 meters a second times 1,000 kilograms per meter cubed. So that this together gives you a mass flow rate of equal to 100 kilograms. Not dividing it by, just underlining it. If you add the specific heat capacity at 4,000, I think it's 138, it is joules per kilogram per degree C, same as degree Kelvin. And if you think of the temperature drop, just to make our life easy, as 100 degrees centigrade, then we can calculate what the heat rate is, which is equal to 100 kilograms per second times 4138 joules kilogram degree C times 100 degrees C. So hopefully in terms of those, kilograms drop out, centigrade drop out, and this becomes 4138 times 10 to the 4 joules per second, which is watts, which is equal to, is that right? Why am I off by a factor of 10? So this is 100, this is 4, this is 41 times 10 to the 6 watts. But that seems to be an order of magnitude off. What have I done wrong? Joules per kilogram per degree centigrade. Oh yeah, this was 100. This is 41. So which is not, it's an order of magnitude off. And so this should be, I don't think, this is actually the thermal heat rate that's out of it. If you multiply this by an efficiency, and if you look at efficiencies, we talked about those last time also. It was in this small figure here, going back a long, long time. So steam turbines, in converting heat energy to mechanical energy, it's something like 40% efficient. In converting mechanical energy to electricity, generators are quite efficient, almost 100% efficient, but this is about 50% efficiency. So the actual output from that is equal to just half of that. So it'd be 20 megawatts, which again is too high. So I don't know what exactly I've done wrong in that particular case. So if you multiply by efficiency, 50% efficiency, going from hot to electricity, gives you 20 megawatts. So, yeah, 4 and 3. Yeah, okay, that's fine. So that's high. So that's not right. It's perhaps, this is 4 times what the minimum needs to be. So maybe we're producing here at a higher temperature than we need to produce. So this, and I won't sort that out this time. So the bottom line is, to be able to do that, we're relying on one thing. We're relying on, well, 2 things really. One is that the components in this equation, we need to have all of them be finite and relatively large, so that together they're all relatively large. If any one of them is small, then it completely kills your reservoir. So if you inject cold water at 40 degrees centigrade and you spend so little time going across your reservoir that it comes out at 40 degrees centigrade, then by definition delta T is 0, and so you don't have a viable reservoir. If you're that would represent the case where the heat transfer area of the reservoir is so low that it doesn't transfer the heat from the rock into the water. if you're unable to get water across the system at any given flow rate, because the permeability of the reservoir is 0, then Q would be small, and then this term would also be 0. So the two requirements that you need are that both the temperature change, the residence time within the reservoir, and the recovery of temperature from that reservoir is large enough, and that a sufficient rate of that fluid is available to that. Typically, the density is controlled by the fluid. People have talked about using CO2, supercritical CO2, as a heat transfer fluid. It's a very exotic idea. It's never been tried in practice, but that's a possibility. Water is relatively cheap and abundant, and therefore it's used for that characteristic. And so the positive properties of water are that, one, the heat capacity is relatively large, higher than CO2 actually, and also that its density is relatively large, also higher than CO2. And so it's a given that if you use water, both the density and heat capacity are large, and you only have to worry about, at specific reservoirs, having a big enough volumetric flow rate and a large enough temperature recovered from the reservoir, which means that you have enough contact of the fluid with the reservoir to be able to do that. So we know that anywhere we go in the Earth's crust, if we go down 4 kilometers, say, if this is 4 kilometers, then even in places, if we think that the lowest thermal gradient, geothermal gradient, is 25 degrees centigrade per kilometer, then we would be at 100 centigrade here, plus the temperature on the surface, 10 or 20 degrees centigrade. Certainly not today, minus 16 centigrade today, but the average temperature on the surface would be represented. If you're at places where it's hotter, plate boundaries, mid-ocean ridges and subduction zones, the west coast of California, then if you went down 4 kilometers, you'd be at 200 centigrade plus 10, so roughly magnitude. So all of a sudden, you double your heat rate in moving from these two different magnitudes. These pretty much exist everywhere around the globe. It's caused by the fact that below this, we're creating heat by radioactive decay and also from the remnant heat of the planet from the Big Bang, when the planet was formed. So this is present everywhere, but the question is whether you can utilize it by removing it to the surface with a heat transfer fluid where it exists on plate boundaries, or where you create the reservoir interior to those. So we'll talk a little bit today about why this geothermal gradient exists and what the controls are, what's its origin in the subsurface. It relates to the little movie we looked at, where it varies and how it varies depending on location, and what the magnitude of that is relative to how you might recover it. So if you know how quickly you can recover it, you can calculate whether it will be depleted or whether the resupply from the base will be sufficient to be able to keep it as a sustainable resource that you'd like to be able to use it for. So those are the kind of questions that we would like to talk about. So this represents the Earth and some facts below it. I guess the Earth, the solar system is something like 13 billion years old from the Big Bang. The Earth agglomerated from gases within the galaxy something like, I think, 4.3 billion years ago. It got hit by a meteorite and formed the moon that now transits around it. And the composition of the Earth comprises a central core at its center, and surrounding that core a mantle, a lower hot mantle, an upper cooler mantle, and then sitting on the surface, everything that we know about it in terms of what we can touch. And that is the continental crust. The continental crust exists on the continents. Ocean crust exists beneath the oceans. The continental crust is the thickest. It may be of the order of about 70 kilometers thick. On the oceans, I guess it's not written here, oceanic crust might be 30 kilometers or so in deep. And this is the crust that is created at these constructive boundaries that Robert Ballard was talking about. So a section through this looks like this. So initially it's transformed from 4.3 billion years ago, when it was just a ball of magma floating around in the universe. Over time, the crust of it solidified and became solid. And as a result of the continuing cooling of this crust, the hot material in here has set up plate tectonics. So what has happened is that the heat in being emitted from this central core is trying to escape through this hot viscous fluid which exists underneath this brittle cap. And just like a pot on a stove, as you heat a pot on a stove, it'll start off static, and as it begins to boil, it will transfer heat from the base of the stove into the fluid above it in the most efficient way it can do, and that most efficient way is by convection, not by conduction. And so what will happen is the fluid at the base will be heated. It will become less dense because it expands as it heats. As it becomes less dense, it rises to the surface. It may squeeze out of the ground at these constructive boundaries by filling up the gap between these two plates as it wells up. As it wells up, some of it will come onto the surface and create the gap between the two plates. We heard that was something like an inch a year, 60 inches in a lifetime, that it pushes these plates apart. If it's doing that on a shell which is present on the surface, there's no room for this to move except for it to buckle the shell and to create a so-called destructive boundary. So some of it will come onto the surface to move this at 1 inch per year, but most of it will be transited underneath the surface, and as it moves across from one location to the other, it'll cool. As it cools, it will sink, and as it sinks, it will go back to the base and to be set up in these convection cells. And so in the same way that a pot on the stove sets up convection cells as the boiling of the water, in much more viscous fluid it's much more orderly, and it would last from the base of the core essentially up to the surface, provide a traction on the base of the surface that pulls this plate along by friction along the base, by push, by the new fluid that's present in this new boundary, and also by the weight of the slab, which tends to pull the slab across and descends into the mantle. And as this plate descends into the mantle, it will slowly melt and rejoin the mantle. So plate tectonics is what's going on the surface of the planet. So I guess these are just the metrics of that. The core is solid iron. It's 1,200 kilometers in radius. This total radius here is something like 6,000 kilometers. So the first 1,000 of that is the iron core, very dense iron core. It's molten to a depth of 3,000 kilometers, so I guess this would be almost down to the core. And the temperature in this is something like 6 to 4,000 Kelvin. So degrees Kelvin is 273, as you probably know. It's not degrees. 273 Kelvin is equal to 0 degrees centigrade. So a degree Kelvin and a degree centigrade are the same, but the scales are slightly offset by the fact that they don't say. The solid plates in terms of continental crust are said are something like 70 kilometers thick. They're thinner on the ocean. And in terms of the heat supply, so the heat supply that comes from the core comes 40% from the material that's in the core from its intrinsic heat from the Big Bang, and 60% from long-term radioactive decay, so the decay of uranium and other transuranic elements. They give off heat as they decay, basically ultimately into lead from those, and that heat is present into the magma which comes onto the surface. So we looked at that. This is what actually we didn't look at this. We looked at Ballard. This is some of the figures here were taken from that location if you want to find them. This is a schematic of exactly what's going on. Hot magma is rising between the plates. It's pushing them apart. It's making these mid-Atlantic ridges. All along this spreading center is the magma squeezing onto the surface. This is under 1,000 meters worth of ocean, so you don't see it, except for places like Iceland, where there's an island that straddles the ridge. It morphs into destructive boundaries, where a subduction zone carries the created plate back into the mantle. It slowly melts as it goes down because it sees it has a longer residence as it goes down. So this may be of the order of hundreds of kilometers. And so the residence time for this is quite long. If it's traveling at 5 inches, 2 centimeters per year, and so if it needs to go, it'll take 50 years to go a meter, and so you can calculate exactly how long it would take to go 100 kilometers down. This cold oceanic crust will tend to carry the cold plume into the subsurface, and so if you chart a contour of equal temperature, an isotherm, then this dotted line, I think, is, say, 300 degrees centigrade. I'm not sure exactly what the number is. At the mid-ocean ridges, it will be elevated because you're bringing magma up to the surface, so you'd expect it to be hot at higher depth. If cold ocean crust is being turned back into the mantle, then you expect that this plate would be cold, and therefore the location of this isotherm would be depressed. The other thing that goes on here is that as this goes down, this includes both solidified magma but also sediments. So this is filled with water. So as this gets carried down, what happens here is that this water is boiled off as it becomes hotter and hotter. So once it gets above, if this is really 300 degrees centigrade, and it's a higher temperature than atmospheric, so the boiling point would be larger than 100 degrees centigrade, which it is in the atmosphere. This water evaporates or is released from the slab and is released into the magma which is here. And the net result of this, if you add water to the magma which is already there, it reduces its melting point, and as a result of that will melt the magma which is in here, which leaves it to be able to upwell and create volcanoes which are on the inside of the continent away from the destructive boundary. And so this could, if you like, be, it doesn't fit very well. This would be Iceland and the Mid-Atlantic Ridge with Iceland straddling that. A better analog for this would be the west coast of the US. So if this was the west coast of the US, the states coming up here would be California, Oregon, Washington, and Canada above that. This would be the Pacific Ocean. This would be the subducting slab going under Oregon and Washington. It turns out that this plate boundary as it goes through California is the San Andreas Fault, and it's not a subducting plate anymore. It's actually a stalled plate which is locked, and it's traveling as a strike slip fault. So this is a fault that is moving only in this direction rather than a slab going underneath. And this, of course, is actually where the geysers are. As this slab goes underneath those states, these states actually would extend much further. This would be the Cascades. So this would be Mount Rainier above Seattle. This would be Mount Hood. This would be Mount Lassen and Mount Shasta in California. And these would be volcanoes, active volcanoes in western US. And around these volcanoes, there'd be the isotherm is elevated, so it's very hot at very shallow regions. And of course, one of the most recent demonstration projects for the US DOE has been Newberry Mountain, which is in Washington State, where we're trying to make hot, dry rock geothermal energy from in the caldera of a kind of semi-dormant volcano which exists. And of course, Mount St. Helens would be one of these as well, which erupted in May 18th, 1980. So that's that. I guess the other thing to note is that also you can get features where you can get upwelling of magma not only in portions of the crust which are in the middle of the ocean, but you can get it on continental areas. So a most obvious region for this, not in the US, would be the East African Rift in Kenya, in Africa, where it's being pulled apart by magma coming up in here. So I guess if you go down here, that would be, so this is a map here. These yellow stars are active geothermal sites around the world. If you look at these individual components, the green arrows are the velocities of the plate as they're being turned across the planet. So this is the Mid-Atlantic Ridge here, all the way down here. The only place where it's exposed is in Iceland, where these multiple plants exist, recovering geothermal energy. This would be the Mediterranean, this would be Spain, Gibraltar, the Mediterranean here. So I don't know whether this is in Turkey or in Cyprus or elsewhere at the eastern end of the Mediterranean. Certainly Turkey has geothermal fields. I think it could be Lardrello. The oldest geothermal field in the world is in Italy. Actually, it could be Italy. This might be Italy here, and this may be the eastern extent of the Mediterranean. Lardrello is the oldest actively recovered geothermal field in the world, maybe from the 1930s in northern Italy, in the Apennines. This is the East African Ridge, which is being pulled apart, and magma is coming up between that, and you get this kind of stair-step behavior that shows here. So the idea is that you have crust that looks like this. You pull that crust apart, and in doing that, you develop kind of a stair-step thing where the surface of this crust drops down in a wedge like this. So this region here is a portion that you keep on pulling it, and maybe this drops down further, so you end up with this kind of stair-step behavior from these blocks dropping down as you extend it. So this is what's happening in the East African Ridge. This is the Red Sea, Hormuz. This is, where else do we have this? This is the Caribbean, Central America, all down Central America. So this is a constructive plate boundary where magma is welling up, including on Iceland. There happen to be constructive plate boundaries in places where there's not a rift, such as hotspots. This is Hawaii, where there's a plume that comes up, and these are geothermal fields on the island of Hawaii. The Canary Islands would also be places where hotspots exist. The whole of the west coast of the US, Central America, El Salvador, Panama, Mexico, etc., are all geothermal. These are destructive plate boundaries. The Pacific plate is going underneath the American plate down here. So this is the Pacific plate going under here. This is another plate, I think it's the Nikos plate, which is also going underneath Chile on this border. So this is a destructive plate boundary also. And, don't know. And this would be Southeast Asia. And so this looks like it's Japan. No, this is Japan, which has geothermal energy. This is the plate boundaries that goes down east of the coast of China. This would be Indonesia off the north coast of Australia. We talked about the Cooper Basin geothermal plant on that bar plot, which is a hot dry rock geothermal reservoir, which is now defunct. I'm not sure what this is, and this would be New Zealand, which is also on the North Island of New Zealand, which is also a pull-apart rift basin, just like in East Africa. So these are the regions of the Earth. So I guess the important point for us to note is these are places, all of these plate boundaries, where the geothermal gradient might be of the order of 50 degrees centigrade per kilometer. Useful for us because it means that to be able to get access to it, you don't have to drill very deeply to get access to it. So it would be at this range here. So if you can drill down 4 kilometers to get to it, then at 4 kilometers you're almost guaranteed the fact that you'd be getting 200 degrees centigrade water, which would allow you to easily to maximize the magnitude of your reserve. If you get down deeper, correspondingly you'd get hotter material and the efficiency of your reservoir would be greater. The rest of the planet exists roughly at this magnitude here, which is of the order of 25 centigrade. So going down 3 or 4 kilometers really only gives you 100 degrees centigrade, which you can flash to steam, but it's not going to be as efficient as these other places. So everywhere else that you see, which would be the continental US, the continent of Europe, the continent of Africa, all of these would be at this lower magnitude of 25 degrees centigrade per kilometer. So this gives us some idea of the distribution of these different components. Clearly, we'd like to be able to harvest it from the hotter regions where it's present hot, high within the crust. And also we'd like to harvest it from these regions because we've already made the supposition that in destructive or constructive plate boundaries, we've got lots of displacement occurring, and therefore the possibility that we're making porosity at the same time as this deformation occurs allows us to easily recover the fluids without sucking too hard on them, pumping too hard. So that's the situation where we are. So that's it. So that's the distribution. So the question then is, why this particular magnitude of the geothermal gradient? What controls this? Well, you could imagine that the gradient is controlled in some respect by how much heat flux you have going across it. So what's the rate at which temperature is able to be forced into the system, and then in the case of the crust, to be conducted across it. We already made the point that conduction is the most inefficient method of heat transfer. We'd much rather, if this was fully filled with a fluid, have it convect, because that would transfer fluid much more quickly. If we have a solid crust which can only conduct, then we're limited to a transfer rate which is controlled by the thermal conduction within the crust. So if we look at the budget, we talked about the relative magnitudes of these. So by radioactive decay, you can imagine if you get radioactive decay from the mantle, the amount of heat energy that's produced is something of the order of 15 terawatts. We also said by happenstance that the fossil fuel budget that we use on the planet is of the order of 10 to 15 terawatts in terms of capacity. So that's roughly the same what we use by using primarily fossil fuels to one of the components of the heat flux in the subsurface. So that is from decay of elements within the mantle and the crust, which is generated here and has to come out because it's hotter in the core. It can only travel outwards to the exterior, which is roughly at 10 degrees centigrade on average as you go around the globe. So the air temperature at the outside is of the order of 10 degrees centigrade. 30 degrees C here in the summertime, air temperature may be minus 20, or I guess that would be minus 10 average in the wintertime. So the difference between -10 and 30, +30, is plus 10 degrees centigrade on average. And primordial heat is the heat that comes from the fact that in the core it exists at a very high temperature, and it comes out of here by conduction from the iron core, and then is convected in the different portions of the mantle as it comes through the system. Okay, 1 hour in. We can look at the relative proportions of these. This is a little cameo of what's going on. A constructive plate boundary that moves apart. A destructive plate boundary that occurs on either side of a ocean basin in this particular case, and the heat that comes out from this. If you look at the elements that give you heat release, you can calculate what the heat release would be if you knew what the proportion of those elements are. I don't know what those are, but if you look at the makeup of heat flow on the surface of the planet. So he said that this is something like 60 terawatts. Not doing that. 60 terawatts worldwide. So this comes from summing up the total that comes out, which is relatively small in comparison. So heat flows, you can see here within the continental crust. Cold crust is smaller, so blues are relatively slow. This is in milliwatts, so 10 to the minus 3. Watts per square meter. And so a cold rate is something of the order of 20 milliwatts per square meter. So you see that pieces of old crust or thick crust within continents are cold. Places where magma is supplied on constructive boundaries, the Mid-Atlantic Ridge, and constructive boundaries offshore off North America are all relatively high. The highest magnitudes of these are of the order of 150 to 200 plus milliwatts per square meter. So this conforms directly to the locations where we expect those magnitudes to be higher. We'll use a couple of books in this class. The one is by Bill Glassley. So the text that is represented by WG in the syllabus is Bill Glassley's text. This is an idealization also of that system. Heat flow on the destructive boundaries, the constructive boundaries for the Mid-Atlantic Ridge, etc., and their magnitudes. And if you look at the US, perhaps this is what we'll finish with today. Yeah, we've got the US. You also see regions which are hot and cold. So what you have here, if we looked at this, this is the Mendocino triple junction. So I wonder if it does it do white? Oh, yeah, it does. Okay. So this here is the San Andreas Fault. Goes down to the interior of Baja California. This is Baja California. So this is the so-called Mendocino triple junction. And so this plate here is traveling underneath Oregon and Washington. Actually, it's going under here. This is the plate boundary roughly here. So it goes under. This is a cold area here. This would be the San Joaquin Valley and the Sierras as you go inland in California. These would be the Cascade volcanoes down here. So this would be Mount Rainier above Seattle. This would be Mount Shasta in Northern California. Hood and Baker. Mount St. Helens would be here in Washington State also. All of this area within the so-called Intermountain West. Where is this? This would be Denver, I think. So this is kind of the front range of the Rockies. So all within the Rockies in Nevada and Utah, this is all high heat flux at the top end of this. As you go to old continental crust in the eastern US, you see the cold regions. If we zoom in, it won't stay open for me, but this little state here is Pennsylvania. We are right here. Green is cold, blue is even colder. So clearly you have to go down. This means that this gradient here is 25 centigrade. This might be 50 centigrade per kilometer gradient here. Later on in the class, you'll see Patrick Fulton from Cornell talking about the Cornell Geothermal Project, which Ithaca is right here. There are a couple of little hot spots. There's one here. There's one that doesn't show up in West Virginia, which is down here. And there looks like one that's right here at Allegheny College, near Erie, which are slightly warmer, but these still aren't very warm. You'll see that in portions of the Gulf of Mexico, these are sedimentary reservoirs that are quite warm. And along the arc of the Windward or Leeward Islands, these are the Caribbean islands here. This again is a plate boundary where cold Atlantic plate is subducting underneath the Caribbean plate and producing these volcanoes that exist as the Caribbean islands. Montserrat is one of these, Soufriere St. Vincent is one of these, etc. All volcanic islands that exist just like the volcanoes inside on the continental crust. Subducting slab goes under, water comes off, it melts the crust, and volcanoes come up from that. In this particular case, the slab subducts under oceanic crust. It melts, water comes off the slab, it melts the upper part of the crust, and it makes volcanoes that come up instead of within the continental crust. They come up as individual islands, maybe separated by 20 or so kilometers along this boundary. And that's it, yeah. And so you have that also. So I'm going to leave it there for now. We'll carry on for this next time. I don't look up very much for questions, but are there any questions?